Hello everyone. Today we'll be studying spin electron spectroscopy. Okay. So let's understand the word. What is spin electron spectroscopy? Okay. So before going to this spectroscopy, what is spectroscopy? Okay. So we have something called as spectroscopy. So spectroscopy is the study of electromagnetic radiation with matter. Okay, so spectroscopy is study of electromagnetic radiation with matter. And so what kind of spectroscopy we are looking at? So we are looking at spin resonance spectroscopy. Okay, we'll see why it is spin resonance spectroscopy. So to know this spin resonance, first we have to know what is spin. Okay, so in an atom, we know there is a nucleus and there are orbit. Correct. And this orbit will have some electrons revolving around it. Correct. So in the first shell there are two electrons. In the second shell there can be maximum 8 electrons. Right. So it follows the rule of 2n square. So now what is spin? Okay, so we know these electrons are revolving around the nucleus. Right. Also we have assumed this electron can spin along its axis. Okay, so it's not like spinning. Uh, since this is a fundamental particle, it is not quite right to tell it is spinning around its own axis. But whenever we observe a isolated electron, it has some intrinsic property called as spin. So even though it is not spinning, but its property shows that it is spinning. So for example, I'll tell you why it's like that. So if we have a charge moving in the circular this orbit, so what happens? There will be current produced due to this charge, and it will have some magnetic moment. Correct. So whenever isolated electrons were observed, okay, whenever scientists conducted the experiment to observe the magnetic field of this isolated electron, even though it is not spinning in the orbit, still they could detect the magnetic moment of it. So that's why we say this as spin angular momentum and this is orbital angular momentum. Okay. So electron has its intrinsic magnetic moment called spin angular momentum. Okay. So here in this chapter we'll be studying the property of the nucleus. Okay. So the nucleus is made up of proton and neutron. Correct. So proton will have charge plus E and neutron is electrically neutral. So 0. So now this proton and neutron, it is also having some intrinsic magnetic moment and it is called spin. Okay. So what we are studying here is, so the electromagnetic radiation, whenever it interacts with the nucleus, okay, so in nucleus there might be proton or neutron. Okay, so what happens is, in some conditions what happens is the spin gets interacted with the electromagnetic radiation and there can be flipping of this spin and the energy will be absorbed by the particle. Whenever the radiation is removed, it returns back to its original position and emitting the radiation. Correct. So this radiation will give the important information about the compound. Okay, so this is the introduction about the topic. Okay, so let's start our discussion in spin electron spectroscopy. So now let's study the nature of spinning particle. So topic 1, nature of spinning particle. Okay, so electrons are belonging to the class of leptons, and proton and neutrons belong to the family of baryons. Correct. These both particles are spin half particles. Okay, so these two exist in the nucleus and this exists outside the nucleus. Okay, if the nucleus is composed of proton and neutron, then the total spin will be vector combination of E plus N. So we know this will have spin half, this will have spin half. Okay, let's take a simple example of hydrogen atom. So this hydrogen atom will have a electron and a proton inside the nucleus, right? So here in this chapter, we'll be studying NMR and ESR. So NMR means nuclear magnetic resonance, and ESR means electron spin resonance. So in nuclear magnetic resonance, our focus will be in the nucleus, and in electron spin resonance, our focus will be on this electron. So first let's study about NMR. So in NMR, okay, we see, let's take this example, proton or hydrogen atom. So now let's observe the nucleus. So nucleus has only proton, correct? And what is the spin of the proton? Spin of the proton is half. Okay, this is simple. So imagine a condition like this, helium atom. So helium atom has two proton and two neutron, right? So how, what might be the overall spin of this particle? Okay, so it can be anything, right? So it might imagine like this: half plus half plus half plus half. Correct. So we'll get two. Okay, this is also possible. So what we're doing here is the spin are vectors, right? So this is half, this is half. Okay, so if this is a of proton and neutron might be there, spin of neutron. Okay, you can add this four vector in any angle, right? There are many combinations. So spins are added by the laws of vectorization. Okay, that's it. Okay, so now we quite don't understand how to add the spin and not add the spin. Okay, we are not sure about how is the interaction, right? So there are some empirical rules to calculate the spin of a element, nuclear spin of an element. Okay, so the first rule is nuclei with both P and N even. So what is P? P is proton, N is even, N is neutron. So proton and neutron number is even. If the proton and neutron number are even, so then they will have zero spin. Okay, so what is an example for this? Helium atom. Okay, so helium atom has two proton, two neutron, and the total spin of this is 0. So how do you know it is 0? So basically perform an experiment. Okay, it is a Stern-Gerlach experiment. Okay, so if you do Stern-Gerlach experiment, you can identify whether it is a integer spin or a half integer spin or zero spin. You can identify it. Okay, so the second rule is nuclei with both proton and neutron number odd will have integral spin. Okay, so if proton and neutron number is odd, then it will have integral spin. Okay, let's take an example. So example is 14 nitrogen. So this is mass number. So nitrogen 14. So this has the spin equal to 1. Okay, so the another rule is nuclei with odd mass number have half integral spin. So odd mass number. So I can take the example of simplest example is hydrogen. So this hydrogen has nuclear spin half. Okay, it consists only proton. Okay, so these are empirical rules. So how can we calculate angular momentum if we know a spin quantum number? So see, the spin quantum number is denoted by I. Okay, this is spin quantum number. Okay, so I will denote angular momentum by the vector I. Angular angular momentum I. So it is given by square root of I into I plus 1 h by 2 pi. So you can write h by 2 pi or h cross. Okay, so you can either write this or this. Okay, both are same. So this is the formula for angular momentum if you know the spin. And how do you get this derivation? You have to find the eigenvalue of L square operator, right? So L is angular momentum. So L square operator, if you find the eigenvalue equation of this, so you will get L into L plus 1, right? So, so basically, this is from quantum mechanics. Okay, so here it is not I square. That's why you took the square root. So square root of I plus I into I plus 1. Okay, so for today, this much is enough. If you have any doubt, you can ask me. Okay, thank you.